All right, let's talk about something that happens billions of times a second, that makes our entire digital world possible, but that most of us never, ever think about. We're pulling back the curtain on the invisible systems that make sure the data you send and receive gets there in one piece.
Of course you have. We've all been there, right? You download something and it's just junk. Or a text message comes through as a bunch of weird symbols. It's annoying, for sure. But the real question isn't why it happens sometimes. It's why it doesn't happen all the time.
And here's the fundamental reason why. The second data leaves your device, it's out in the wild. It's vulnerable. That journey it takes, whether it's flying through the air as Wi-Fi or zipping down a cable, is basically a digital minefield. Things can go wrong. And the stakes can be incredibly high. I mean, a corrupted photo is a bummer, but imagine this scenario. A single tiny error in a bank transfer could be an absolute catastrophe. When it comes to things like finance, accuracy isn't just a nice to have, it's everything.
Okay, so let's dive into that. To really get why the solutions work, we've got to understand the problems first. So what's actually going on out there on this digital obstacle course?
Well, our data has a few main enemies. You've got electrical interference. Just think of it like static on the radio, but for your data. Then you have issues with packet switching, where the little chunks of your data can just get lost, or even weirder, duplicated along the way. And finally, there's data skewing, which is when bits that are supposed to arrive together get out of sync, and the whole message just turns into gibberish.
So, with all these threats out there, how do we possibly fight back? Let's start with the first line of defense, some of the simple but really clever little watchdogs that are designed to spot trouble right away.
First up is something called a parity check. This is a classic, and honestly, it's a wonderfully elegant idea. The whole concept is to just add one single extra bit, the parity bit, to every single byte of data, and that one little bit can tell you if something's gone wrong. So here's how it works. Let's say the sender and the receiver agree on a rule. We'll call it even parity. So the sender looks at the byte, it counts the number of ones. In this case, there are 4, which is an even number. Perfect. Since it already matches the rule, the parity bit gets set to 0. Now, on the other end, the receiver does the same count. If just one of those bits got flipped on the journey, the count would suddenly be odd. And bam, it knows an error happened. Super fast. But here's the catch. If 2 bits flip, the count goes back to being even, and the error slips right by. Okay, next we have the Echo check, and this one is about as simple as it sounds. The device that gets the data just sends a complete copy of it right back to the sender. But, and this is a big but, this method has a huge flaw. If the data that comes back is different from what was sent, you know there was an error, but you have no idea where it happened. Did the data get corrupted on the way to the receiver? Or was it fine on the way there but got corrupted on the way back? The sender is just left scratching its head, which makes this whole thing pretty unreliable. So because those simple checks have their limits, we need some more sophisticated, heavy-duty ways to find these errors. And these are the techniques that really power the modern internet we use every day. This brings us to the checksum. Now, the best way to think of a checksum is like a unique digital fingerprint for a whole block of data. Instead of just looking at one byte, the computer runs a special calculation on a bigger chunk of data to create one final value that represents the whole thing. So the process is basically a 5-step dance. The sender calculates the checksum, the fingerprint, and sends it along with the data. The receiver gets the data, and it runs the exact same calculation to create its own checksum. Then it compares the two. If they match, awesome, the data's good. If they don't match, it means something changed, and a request goes back to resend that block. This is way more robust than a parity check because even a tiny change in a big block of data will create a totally different fingerprint. Now for a different kind of detective, one you've probably encountered thousands of times without even realizing it, the check digit. We see these on barcodes, on book numbers, you name it. This isn't about data flying over a network. This is all about catching common human errors when we type stuff in. And what's so brilliant about this is that it's specifically designed to catch the exact kind of clumsy mistakes we all make. You know, you type an 8 instead of a 3, or your fingers get tangled and you type 57 when you meant 75. That's a transposition error. The math behind the check digit is set up so that these common slip-ups will almost always result in an invalid code, catching the mistake right at the source. Okay, our final method, automatic repeat request, or ARQ, is a little different. It's less about a single clever calculation and more about setting up a protocol. Think of it as a set of rules for having a very clear and reliable conversation. So just picture this conversation. The sender starts by sending a packet of data. It's basically saying, okay, here's the first piece of information.
Then, the receiver gets that packet. It runs its own checks, probably a checksum, and if everything looks good, it sends back a positive acknowledgement. That's the technical term for, yep, got it, it looks perfect.
And only when the sender gets that all-clear signal does it know it's safe to move on. It says great and sends the next packet in the sequence.
But what if a packet shows up damaged? Well, then the receiver sends a negative acknowledgement, which is the polite way of saying, uh-oh, something's wrong with this one, please send it again. And the really smart part is that ARQ also uses a timeout. If the sender sends a packet and hears nothing back, no positive, no negative, just silence, it assumes the packet got lost and just automatically sends it again. This whole system makes communication incredibly reliable.
So we've gone from simple parity bits all the way up to these complex, polite conversations between computers. Let's zoom out. What's the big picture here? Why does any of this actually matter? Here's the bottom line. These methods are the absolute, unsung heroes of the internet. They are the invisible guardians working tirelessly in the background. In those few milliseconds it takes for a web page to load, these systems are checking and rechecking to make sure everything you see and do is exactly as it should be. They are, quite literally, the foundation of digital trust. And that leaves us with a final, really cool thought. We depend on all this for communicating across town or across the planet. But what happens when we're trying to send data across millions of miles of empty space to a rover on Mars? The potential for errors, the massive time delays, it's a whole different ballgame. How are these data guardians going to have to evolve to protect information across those vast cosmic distances? That's a huge challenge that engineers are tackling right now, building the next generation of guardians for an interplanetary future.